In the vast Pacific Ocean, a concrete dome sits silently on a remote island, holding one of the world's most dangerous secrets. This isn't just any ordinary structure. It's cracking, leaking, and rapidly becoming uninhabitable as ocean waters rise around it. Inside lies 105,000 cubic yards of radioactive soil and debris from nuclear weapons testing, measured during the 1977 to 1980 cleanup that cost 6 servicemen their lives and left hundreds more with radiation-induced cancers. As we enter 2025, scientists are sounding unprecedented alarms about the high levels of plutonium-239 still trapped inside. The Marshall Islands Cactus Dome has transformed from a containment solution into what experts now call a nuclear time bomb, threatening the entire Pacific ecosystem. The structure that was supposed to provide permanent protection is now failing in ways no one anticipated. The concrete tomb that's falling apart. Built to contain nuclear waste for eternity, the dome now reveals the fatal flaws in its construction with each passing storm. The 2025 structural assessment reveals a dome in severe distress, with 187 of its 357 concrete panels showing significant deterioration. These aren't minor surface blemishes anymore. The concrete slabs that once fit together like a giant puzzle now display gaps large enough to slip a hand through. Water stains streak down the dome's surface, marking where Pacific storms have repeatedly battered the structure over nearly 5 decades. The concrete itself tells a story of miscalculation. When construction began in 1977, engineers used standard Portland cement mixed with local coral aggregate. This seemed practical at the time, but local materials introduced chlorides that accelerated corrosion within the concrete matrix. The dome's 18-inch thick walls were designed to withstand tropical storms, not the supercharged hurricanes that climate change has unleashed across the Pacific. Each major storm system brings winds exceeding 135 miles per hour in recent hurricanes, creating pressure differentials that flex the concrete beyond its design limits. Salt water has proven to be concrete's most relentless enemy. The Pacific Ocean's corrosive mixture has spent decades penetrating the dome's porous surface, with chloride ions attacking the steel reinforcement bars embedded within the concrete, causing them to expand as they rust and crack the concrete from within. Vegetation has discovered these weaknesses and exploited them mercilessly, with coconut palms and invasive shrubs taking root in the dome's cracks, their expanding root systems creating hydraulic pressure that splits concrete panels apart. The dome's original specifications assumed a stable climate with predictable weather patterns. Engineers calculated stress loads based on historical data from the 1950s and 1960s, when Pacific storms were less intense and temperature variations more moderate. They never anticipated the thermal cycling that now occurs daily. Morning temperatures of 78 degrees Fahrenheit give way to afternoon highs exceeding 95 degrees, causing the concrete to expand and contract repeatedly. This constant movement has opened hairline fractures that now measure several millimeters wide. The dome's trapezoid panel design, once considered innovative, has become a structural liability. Each panel relies on its neighbors for support, creating a system where failure in one section compromises the entire structure. The joints between panels were sealed with bituminous compounds that have long since deteriorated under constant UV exposure and temperature fluctuations. These failed seals allow water to penetrate the gaps, creating internal pressure that pushes panels apart from within. Surveys from 2008 through 2020 consistently found widespread cracking, spalling, biological growth, and 2 exposed panels requiring repair, yet determined the dome nominally functional. The 2018 drone survey identified 46 cracks and 36 spalls that required immediate repair, with a 2019 Hamilton drone inspection revealing that 2 panels had left waste exposed before being repaired. Recent assessments show 43 panels displaying severe spalling, where chunks of concrete have broken away from the surface. The largest spall measures 8 feet across and 3 inches deep, exposing the steel reinforcement underneath. This exposed metal shows advanced corrosion, with rust stains bleeding through the surrounding concrete. Pacific storms have intensified dramatically since the dome's construction. Category 4 hurricanes, once rare in this region, now occur with increasing frequency. The dome has endured direct hits from 7 major storms since 2018, each one causing visible damage that accumulates over time. Storm surge has repeatedly washed over the dome's surface, depositing salt crystals that continue corroding the concrete long after the weather clears. The dome's drainage system, designed for normal rainfall, cannot handle the massive water volumes that modern storms deliver. Climate change has introduced conditions that the dome's designers never imagined. Sea spray now reaches the dome's surface during normal weather, carrying salt particles that settle into every crack and crevice. The structure experiences over 200 freeze-thaw cycles annually, not from temperature changes, but from the rapid evaporation and condensation of salt water within the concrete matrix. This process creates internal stress that weakens the concrete's crystalline structure. Ground-penetrating radar reveals that cracks extend deep into the dome's structure, some reaching the radioactive debris below. These fissures create direct pathways for contaminated groundwater to reach the surface and for surface water to penetrate the waste repository. The dome's foundation, built on porous coral limestone, has settled unevenly as underground cavities collapse. This differential settlement has created stress concentrations that manifest as new cracks appearing monthly. The dome's deterioration has accelerated exponentially since 2020. Cracks that remained stable for decades suddenly began expanding at rates measuring several millimeters per year. The concrete's compressive strength has dropped from its original 4,000 pounds per square inch to less than 2,800 pounds per square inch in the most deteriorated sections. This represents a 30% loss of structural capacity, approaching the threshold where engineers classify concrete as structurally compromised. Repair efforts have proven futile against the dome's relentless deterioration. Crews have attempted to seal cracks with epoxy injection, but the hostile environment breaks down synthetic materials within months. Concrete patching fails as new cracks appear faster than old ones can be repaired. The most recent maintenance assessment concluded that permanent repairs would require removing and replacing entire sections of the dome, a task made nearly impossible by the radioactive environment beneath. The dome's current rate of deterioration suggests complete structural failure within 15 to 25 years. However, this timeline assumes current environmental conditions remain stable. Each major storm now causes damage that would have taken years to accumulate under normal conditions. Yet even as engineers debate repair strategies, a more immediate threat emerges from an unexpected direction. When the ocean swallows paradise. Rising sea levels have transformed this nuclear waste repository into an underwater time bomb. Runit Island is vanishing beneath the Pacific Ocean at a rate that scientists once thought impossible. The Marshall Islands face sea level rise measuring approximately 3 inches total rise since 1993, or about 0.1 inches per year, locally over double the global average. This acceleration has transformed what seemed like a distant threat into an immediate crisis. The island that hosts the Cactus Dome has lost 11% of its surface area since 2000, with entire sections of coastline disappearing during major storm events. Satellite imagery from 2025 reveals erosion patterns that continue advancing inland with each passing year. The dome's precarious position becomes clear when you understand the numbers. At just 25 feet above current sea level, the structure occupies what engineers now classify as the flood zone. This elevation seemed adequate in 1977, when planners assumed sea levels would remain stable for centuries. The Marshall Islands' unique geography compounds this vulnerability. The nation's highest point reaches only 33 feet above sea level, making every inch of elevation precious. The dome sits on coral limestone that formed over millennia, but this foundation proves increasingly unstable as ocean chemistry changes and wave action intensifies. king tides have become the dome's most persistent enemy. These exceptionally high tides occur when the moon's gravitational pull aligns with seasonal patterns, creating water levels that exceed normal high tides by 2 to 3 feet. During the 2024 king tide season, ocean water washed over the dome's lower sections for 6 consecutive days. Local monitoring stations recorded water depths of 18 inches across the dome's southern approach, turning the access road into a temporary lagoon. These events repeat monthly during peak tidal periods, each time depositing salt and marine debris across the concrete surface. The dome now experiences a daily rhythm of contamination exchange that transforms it from a containment structure into a radioactive tidal pool. Morning low tides reveal water stains and salt deposits marking where Pacific waters penetrated the structure's base. As afternoon high tides arrive, ocean water flows through the dome's compromised foundation, mixing with contaminated groundwater before flowing back into the lagoon. This process creates a continuous cycle where radioactive materials leach from the dome's interior and disperse into the surrounding marine environment. Water sampling conducted in 2025 detected elevated plutonium levels in tidal pools surrounding the dome, confirming that contamination now moves freely between the structure and the ocean. Storm surges have evolved from occasional threats into regular assaults on the dome's integrity. The 2020 Department of Energy report concluded that storm surge flooding represents the most immediate impact on the dome's structural integrity. Hurricane Naya in October 2024 produced a surge measuring 12 feet, completely submerging the dome for 14 hours. The storm's 165-mile-per-hour winds drove waves directly over the structure, scouring away protective vegetation and exposing vulnerable concrete sections. Post-storm assessments revealed that surge forces had displaced 2 concrete panels, creating new pathways for water infiltration. While surge events have intensified, engineers note that complete structural collapse is not yet imminent. The dome now endures what scientists term sunny day flooding, where high tides cause inundation even during calm weather. This phenomenon occurs when astronomical tides combine with seasonal sea level variations, creating conditions that exceed the dome's drainage capacity. During these events, seawater pools in the dome's lowest sections for hours, slowly percolating through cracks and joints. The frequency of sunny day flooding has increased from occasional occurrences in the 1990s to monthly events today. Meteorological records show that 2024 produced 47 sunny day flooding episodes, compared to just 12 in 2010. Sea level projections paint an alarming picture of the dome's future. Current measurements show Pacific waters around the Marshall Islands rising at rates significantly exceeding the global average. This acceleration reflects thermal expansion of ocean water and increased ice melt from Greenland and Antarctica. Conservative projections suggest the dome will face permanent inundation by 2055, while more aggressive climate scenarios push this timeline to 2045. The Intergovernmental Panel on Climate Change's latest assessment indicates that sea levels could rise 5 feet by 2100, which would submerge the entire dome beneath 35 feet of water. Saltwater intrusion has become the dome's most destructive force, accelerating concrete degradation through chemical processes that engineers are only beginning to understand. Pacific seawater contains 19,000 parts per million of chloride ions, which penetrate concrete through microscopic pores and attack embedded steel reinforcement. This process creates iron oxide that occupies 2.5 times more volume than the original steel, generating internal pressures exceeding 15,000 pounds per square inch. The dome's concrete shows advanced stages of chloride-induced corrosion, with rust stains bleeding through surface layers and chunks of concrete spalling away from reinforcement bars. The dome's foundation sits on porous coral limestone that acts like a sponge, drawing seawater beneath the dome and then releasing it back into the lagoon. This geological formation creates a massive reservoir of contaminated groundwater that fluctuates with ocean levels. Hydrogeological surveys reveal that saltwater now penetrates deep into the island's freshwater lens, bringing corrosive seawater into direct contact with the dome's base and accelerating deterioration of the foundation, while creating underground channels for contamination to reach the ocean. Temperature variations caused by tidal cycles create additional stress on the dome's structure. Seawater temperatures range from 78 degrees Fahrenheit during nighttime low tides to 95 degrees during afternoon high tides. This 17-degree variation causes concrete to expand and contract repeatedly, opening microscopic cracks that grow larger with each cycle. Saltwater cycles and thermal cycles both stress the concrete, creating fatigue that manifests as visible cracking and structural weakness. Wave action during storms has carved channels through the coral limestone surrounding the dome, creating preferred pathways for water flow that concentrate erosive forces. The largest channel measures 200 feet long and 15 feet deep, directing storm surge directly at the dome's most vulnerable sections. Oceanographic modeling shows that these channels amplify wave energy, creating hydraulic forces that exceed the dome's design specifications by 300%. Each major storm deepens these channels, concentrating future wave attacks on the same structural weak points. The dome's transformation from a land-based containment structure to a marine hazard represents an unprecedented challenge in nuclear waste management. Maritime law provides no framework for regulating submerged radioactive sources, creating legal ambiguities about jurisdiction and responsibility. International shipping lanes pass within 50 miles of the dome, raising concerns about navigation safety and contamination of commercial vessels. As the Pacific Ocean steadily claims this concrete tomb, the question is no longer whether contamination will escape, but how much has already begun its journey into the world's largest ocean. The invisible killer spreading through Pacific waters. The radioactive contamination that everyone fears is already spreading through Pacific waters, and the evidence grows stronger with each passing month. While 2015 groundwater sampling found only low levels of radioactivity, more recent investigations reveal a troubling pattern. The 2019 Los Angeles Times and Columbia University expedition discovered localized pockets of contamination comparable to levels found at the edge of the Chernobyl exclusion zone. These readings represent concentrated hotspots rather than widespread contamination, but they confirm that radioactive materials continue leaking from the deteriorating structure. Marine monitoring stations now record elevated plutonium signatures in water samples taken during both high and low tides, indicating continuous release rather than episodic contamination events. Plutonium-239 lingers for tens of thousands of years, so any leak has permanent implications. This element represents the most persistent threat among the radioactive isotopes escaping from the dome, meaning that contamination will continue threatening marine ecosystems long after human civilization has potentially transformed beyond recognition. The dome contains an estimated 3.1 tons of plutonium mixed with contaminated soil and debris, representing enough radioactive material to contaminate vast areas of ocean if released in significant quantities. The bioaccumulation process transforms low-level contamination into concentrated doses as radiation moves through marine food webs. Microscopic phytoplankton absorb dissolved radioactive particles from seawater, concentrating these materials in their cellular structures. Small fish consume massive quantities of contaminated plankton, accumulating radiation in their tissues at levels significantly higher than surrounding water. Larger predatory fish then consume smaller contaminated fish, further concentrating radioactive materials in their organs and muscle tissue. This process creates a pyramid effect where apex predators like tuna and sharks carry radiation loads far exceeding the water they swim through. Pacific Ocean currents create pathways for contamination to travel distances that dwarf the Marshall Islands' tiny land area. The North Equatorial Current flows westward past the dome at speeds reaching 0.5 meters per second, carrying dissolved radioactive materials toward the Philippines and Indonesia. The Kuroshio current system can transport contaminated water northward toward Japan and eventually across the Pacific toward North America. Studies of global fallout transport show that toxic plumes can travel via the North Equatorial Current to reach the US West Coast in about a decade. These same currents that once carried coconut seeds between Pacific islands now serve as highways for invisible contamination. Fish and marine life around the dome now show measurable radiation signatures that confirm ongoing contamination. Initial studies detected trace levels of radioactive isotopes in marine organisms, though these readings fell below international safety limits, according to Bruhl's 2015 marine radioactivity findings. However, more recent sampling reveals increasing contamination in specific species. Coconut crabs, which feed on organic matter washed ashore, show elevated plutonium concentrations in their tissues. Sea turtles that nest on beaches near the dome carry radioactive isotopes in their shells and organs, spreading contamination to nesting sites throughout the Pacific. Even coral polyps growing on the dome's exterior surface have incorporated radioactive materials into their calcium carbonate structures, creating a permanent record of contamination in the reef ecosystem. Understanding radiation exposure requires distinguishing between external and internal contamination pathways. External exposure occurs when radioactive materials emit energy from outside the body, similar to receiving an X-ray. This type of exposure can cause radiation burns and increase cancer risk, but the effects typically end when the source is removed. Internal exposure happens when radioactive particles enter the body through ingestion, inhalation, or open wounds. These internalized particles continue emitting radiation directly into surrounding tissues for years or decades, causing cellular damage that accumulates over time. Internal contamination poses significantly greater health risks because the radioactive source remains in constant contact with vital organs and cannot be easily removed. Cesium and strontium isotopes affect human health through different biological pathways than plutonium contamination. Cesium-137 mimics potassium in biological systems, spreading throughout the body and concentrating in muscle tissue. This isotope emits gamma radiation that can damage DNA and increase cancer risk, particularly in rapidly dividing cells. Strontium-90 behaves like calcium, depositing in bones and teeth, where it continues emitting beta particles for decades. This bone-seeking isotope increases the risk of leukemia and bone cancer, while potentially affecting blood cell production in bone marrow. Plutonium poses the greatest internal threat because it concentrates in the liver, lungs, and bones, emitting alpha particles that cause severe cellular damage despite relatively low penetration distances. Detecting radioactive contamination in marine environments requires sophisticated equipment and techniques that challenge even experienced researchers. Standard radiation detectors cannot distinguish between different isotopes, requiring expensive mass spectrometry analysis to identify specific contaminants. Water samples must be concentrated through complex chemical processes to achieve detectable levels, often requiring 100-liter samples to measure contamination accurately. Marine organisms present additional challenges because radioactive materials distribute unevenly throughout different tissues and organs. Alpha radiation from plutonium penetrates only a few centimeters through water, making detection difficult unless sampling occurs very close to contamination sources. Ocean chemistry complicates contamination measurement because salt water interferes with many detection methods. Chloride ions in seawater can mask radiation signatures, while temperature and pressure variations affect instrument calibration. Radioactive particles bind to organic matter and sediments in ways that alter their detectability, sometimes concentrating in locations far from their original source. Storm events can redistribute contaminated sediments, creating temporary hotspots that disappear before monitoring teams can document them. The dome's location in tropical waters means that detection equipment must withstand corrosive salt spray, high humidity, and intense UV radiation that degrades sensitive electronics. The irreversible nature of oceanic contamination represents perhaps the most sobering aspect of the dome's failure.